Office. We appreciate you coming in today, and we just want to jump into the briefing. So thank you, gentlemen, for coming.
You got to control the slides.
They're in front of Ed.
That's easy. Wait. Thank you. Jason, thank you very much for hosting this briefing. I really appreciate Manufacturing Caucus hosting us, not just now, even in the past, and when we release our reports. So greatly appreciate this opportunity. Thank you all for coming here. Really appreciate your time. And of course, none of this would have been possible without these real experts. So before we get to the real experts and to the main topic of today, without wasting too much time, I want to give you a quick overview, very briefly, about who we are, what we do, broader picture, and then turn it over to the real panel here. So as you can see on the screens on both sides, we are federally funded by NSF and NIST. Thanks to Dr. Bruce Kramer, who's here, our sponsor from NSF, and Mike Molnar couldn't be here. But so we are funded by the federal government to serve as the voice of the advanced manufacturing community, to essentially focus strictly on the U.S. manufacturing competitiveness. And I'll just briefly explain to you what exactly we do and how we do it. So we go to the right.
Different clicker.
What is that?
There we go.
Also, real talented people working for us. Thank you. So, yeah, we're a really good team, you can tell. All right. So, essentially, what we do is to accelerate technology innovation and manufacturing innovation. The two things we do, broadly speaking, is we convene researchers and practitioners, as we've done in this case as well. Identify what are the ideas worth scaling. We've done a lot of basic research, and now how do you move it to the next phase? So what are the ideas worth scaling is all the deep vertical technical topics like the work we've done in the past on biomanufacturing and certainly on the metamaterials, and you'll hear a little bit about that as well today, and high entropy alloys. These are just a few examples. On the other hand, we also look at what are the cross-cutting challenges that are worth addressing by listening to industry, large and small, across all different sectors. A good example of that is the cybersecurity for manufacturers, which is an important topic whether you're making medical devices or airplanes. So, in fact, we put out a report on that as well. And the focus is not just to write some fancy reports, but also to take these ideas to fruition, to the next stage in terms of moving them beyond R and into development, into translational R&D to take it to the next step, because these are obviously the ideas worth scaling. So we need to figure out how to scale. So what we do in all of the work is, before I get to the 4 phases, I also want to point out that we have a leadership council, 38 members, half of them from industry typically. We can see they cover all different sectors, many different sectors. And they're typically the vice presidents for R&D type of folks who are engaged, actively engaged with us and serve as an advisory council for us. And also we have nonprofits through them. Actually, we reach out to tens of thousands of members when we are looking for subject matter experts, or whether we are looking for to disseminate our ideas and so on and so forth, or when we organize workshops. And we have some thought leaders from academia as well. So the 4 phases, what we do is discover, prioritize, develop, and disseminate. In terms of discovering, again, we engage with existing professional societies, trade organizations, federal agencies, who are already doing work, and then who are already hosting big conferences where 3,000, 10,000 researchers come in, and we piggyback with them and then organize like we did that with TMS on one of the topics here. So we work with them in identifying the game-changing ideas first. So we have several, we've done a number of them and there's many more. I don't need to go into details because I want to wrap this up very fast. So just so that you know that we work with existing organizations in collaboration to move the ball forward. And then in terms of developing, before I go to develop, this is one point I want to make very clearly. There are lots of ideas, lots of great ideas, but then when our criteria, whether it's an idea or a challenge, is we have a criteria that says, if this topic were to, if we are wildly successful, is it going to make a big difference to the economy or national security? And why should government invest money into this? Is there why isn't private sector doing it? Is there an opportunity for pre-competitive R&D? If we do, if you are successful, is it really going to give the U.S. the first mover advantage? So we do the international benchmarking. So we ask these tough questions and criteria to our leadership council as well as the members, the experts, in coming up with not just a bunch of ideas, but also which topic we should work on. Once we do that, we go into detail developing the topic like we're doing here today. And most of, in fact, all of our workshops, typically 50% industry, 25% academia, and 25% government. That's our typical mix. And typically our reports have what are the R&D, what are the next steps? That's the important part, the technical focus. As you know, our think tank, we're just strictly focused on the technology side. So the R&D priorities and what are the platform technologies, what are the enabling tools that we need to really invest in? And prioritize them, not a laundry list of 100 of them. And then, but also what are the implementation challenges? It's just not that we're going to develop this and hand it over to our friends in other countries, but how do we implement them here? And what are the policy challenges? That's typically how we address it. We cover these three topics in our reports. And this is just a picture to show that for the last year and a half or so, we had I don't know, close to 2,000 people who participated in different events that we organized, and we had representing lots of different states, and that's quite not updated yet. That there are more stars. So the stars represent where we held events, and there are a few other places as well. And then the contributors come from various sectors, from automotive to you name it, in all different sectors. So I just want to flash that slide up there. And then when it comes to dissemination, this is a great opportunity again, and thank Manufacturing Caucus for doing this every time we release a report. But also by design, we brief federal agencies, like we've done one at DOE yesterday, and we're going to do DOD later today. So, but in addition to that, we actually work with the professional societies and reach out to academia, and then share with them our findings and recommendations as well as with the private sector through National Association of Manufacturers. We disseminate our findings and recommendations. And this is just one topic I want just to point out. The grand challenge that we worked on for several months, had roundtables in many cities, or spent over 1,000 hours of discussing potential solutions. The grand challenge is we've been living in this paradigm of innovate here, manufacture over there. That has reached its logical conclusion of innovate there, manufacture there. That is a real grand challenge underneath it all. This is something that we have a lot of R&D moving overseas, and we need to figure out how we can add value here, create jobs and national security and all other challenges. So I just want to point that out. There's a report that you can find. All these reports are on our website, and a number of reports are outside that you can take a look at it as well. And before I turn it over to Ed Herdnick, I wanted to thank you all once again. Thank especially to these panelists for taking their time, not just coming here today, but having worked on these reports very diligently. And I want to most importantly thank our staff, my colleague and partner Tom Mahoney, where are you, Tom, Associate Director. Oh, Mike's here, our Executive Committee Chair, Mike Russo, and Christine Andrews for doing all the stuff for our Managing Director, and Josh over there, the guy, the primary researcher, and then put a lot of work into these reports as well, and I want to thank you all for coming. Just one last point I want to point out is that Tom and I were asked to brief Pentagon at noon, so we're going to be leaving at about 15, but trust me, none of you will miss us. We got real experts here. And then, actually, Josh, you're going to moderate Q&A, right? Super. With that, we're going to take it from here, and then if you could introduce yourself, and then and each one of you, and then we'll continue the panel.
Okay, sounds great. Thanks, Sridhar. Thanks, everybody, for coming. Nice to see some familiar faces in the audience and lots of new faces as well. My name is Dr. Ed Herdnick. I lead the 3D printing program at the Industrial Research Lab in the College of Engineering at The Ohio State University. But really excited to be here and brief on this report that I participated in, Harnessing Materials Innovations to Support Next Generation Manufacturing Technologies. And I'm here because I participated in the report, and I'm also an active member in a group called TMS, the Minerals, Metals, and Materials Society, which is a 13,000 member international professional society consisting of industry, academic, and government researchers. They're all thought leaders in really driving materials and manufacturing innovation forward. So Sridhar talked about why manufacturing is important to the economy. This has really been my career passion, and just because it's really exciting to me, but thinking about manufacturing in the context of the national economy and national defense, I think it's always great to get grounded with numbers. So if you look at overall GDP and employment, manufacturing is about around 10% of both. And if you look at the Department of Defense budget, about 20% is procurement of manufactured goods of one bit or another. So this is a large proportion of both our commercial economy and national defense. So it's really critically important. And as Sridhar mentioned, there's the innovation piece, there's also the manufacturing piece. So this is just an overall foundation for competitiveness. Now my particular passion is materials innovation. And when we talk about it amongst ourselves in the materials community, I think we kind of take it for granted that materials is important at each step in the manufacturing process. And I just kind of want to frame this up around the report and introduce that to folks in case you're not a member of that materials and manufacturing community. Because materials innovation, when we talk about it, is a lot more than just the steel that you make a car with, or the nickel that you make a jet engine with, or the titanium that you make an implant with. It's the whole value stream. It's how you machine those parts. It's the data and analytics that we're increasingly using to design new alloys, and Chris and Dan are going to talk about that. It's also when we put manufactured products into the field and how we connect those up to the industrial internet and edge devices, and how we measure things and do data and analytics on engines and airplanes and other manufactured goods. So that's kind of the main point I want to start with here, is that material science and engineering innovations are critical to manufacturing competitiveness. So we convened this group of experts in Pittsburgh, Pennsylvania last fall, and the overarching goal that we had for this particular report was to ask the question, or I should say to answer the question, what are the most significant opportunities for materials innovations to unlock the next wave of US manufacturing? So at this workshop in Pittsburgh, we had about 40 attendees, so I was there. We had about half industry, a quarter academics, and a quarter government scientists. And again, I emphasize that because I think it's a really important note in terms of this interaction between all these different thought leaders with different goals, but coming together to really talk about US manufacturing competitiveness. And just to give you a flavor of the attendees, there were large companies like GE Aviation, gave kind of a framing keynote, Lockheed, Boeing. There were small companies like Fabrasonic, which is an additive manufacturing startup, Citrine Informatics, which is kind of a data analytics discovery, materials discovery company. There were other academics, so I'm from Ohio State, Iowa State, Case Western, Carnegie Mellon, and others. And then in terms of the government representation, there was DOE, NSF, Navy, Air Force, and others. So just to give you a flavor of who was there in the room. So we got together for a day. We came up with lots of ideas. Actually, in the report, we came up with 60 different topic areas. So we actually had more ideas than attendees. So again, we all have our different ideas. But we down selected into high priority areas, and this is kind of what Sridhar was talking about, to focus the conversation. And we had 4 points of evaluation criteria. So timeline, so it had to lead to innovation in the next 5 to 10 years. Had to provide taxpayer ROI, has to need public support for pre-competitive investment. So this can't just be things that venture capitalists or again some large company would just go do as a research program. And it also has to favor the US advantage on our current supply chain and current needs. So evaluating those 60 ideas, which are all included in the report, we down selected to 7 high priority areas of research. And within those 7 areas, technology breakthroughs were identified that could really blow open these different fields. And so I think that's what's really important for these reports, where I find them really useful, especially now that I've left industry, I'm in academia, is to come up with what are these critical research areas that are going to be the upcoming SBIR, STTR topics that I can work with our small businesses with, that our Department of Defense stakeholders are going to be interested in, or really where is industry going. So I'm just going to read through the 7 topics, and then in my slides here, I have a little bit deeper dive in 3 particular areas. So just going through the list, the first one was non-destructive evaluation and sensors. The second one was joining of dissimilar materials. Third one was machine learning for accelerated materials discovery and design. Fourth one was qualification of new materials and processes. Fifth one was next generation conductive materials. Sixth one was materials for smart manufacturing and digital thread technologies. And the 7th one was smart materials. So again, in each of these areas, then there's a little bit deeper dive kind of framing up where we thought some potential breakthroughs could be. So the first one of the 3 that I'd like to do a little bit deeper dive on is next generation conductive materials. Why this is important. So one of the areas people might not necessarily think about conductive materials is for lightweighting and transportation. So if you think about ground transportation, commercial vehicles, self-driving cars, electronics is taking up a greater and greater proportion of the weight in vehicles. And certainly this is true on the defense side as well. If you think about JSF and drones and all these new commercial aviation systems, lightweighting of the conductive materials could really be a big breakthrough. Of course, this is also important for infrastructure, for things like grid technology and renewable energy as well. So a couple areas that were identified were superconducting materials and novel covetic nanomaterials, coatings and dielectric insulators, and conductive materials for energy storage and harvesting. Next area I'd like to talk about is qualification for new materials and processes. So again, this kind of goes back to when I was making the opening remarks about what is materials innovation, what is materials science and engineering. This is an area that people outside the community might not necessarily recognize as materials innovation and how critical it is to manufacturing. And this is really, really important because in order to field new technologies and get them commercialized, get them industrialized, it can cost $5 to $10 million for a single new alloy chemistry and process just to get those introduced, let alone manufactured. So this is a really huge barrier for industry, again, whether commercial or defense, to actually introduce these innovations. And so we identified a couple of breakthrough areas. So one is best practices, and 2 critical ones really in terms of the technology space. Model-based qualification approaches for computational materials testing. So how do we buy down that $5 to $10 million to get things introduced? And also sensors and data-driven analytics to enable rapid qualification approaches. So how do we take data, connect it to the industrial internet, and do data and analytics? The third one that I want to talk about, and I actually have 2 slides on this one because this is the next deep dive study that we're going to do, is around non-destructive evaluation and sensors. So again, this is an area that people might not necessarily recognize as being part of materials innovation, but it's really, really critical to industry. So in the same vein as verification and validation and qualification, if you don't have an NDE plan, you can't introduce new hardware into the field. It just won't happen. So this is a key enabling technology, and a couple different areas that we identified were novel sensing technologies and real-time sensing, data mining, compression, storage, and management. So I'm in the field of metal 3D printing. I have some really fancy sensors on my metal 3D printer that watch the melt pool. So as I'm growing these parts, at every element, at literally I think it's 1,000 hertz or something, we're taking a measurement. So in a part that it takes me 2 days to print, I get a multi-gigabyte file. In a big part that I might make for an industrial customer, I might print for 4 weeks, and I might get a file that's multiple terabytes of data for a single part. And this isn't like for the whole manufacturing run, this is for a single serial number part. So that's a really, really important area. And the other one is predictive modeling. So this kind of goes back to that digital thread piece. So what are the physics that I can predict what kinds of manufacturing defects I might be looking for and what I might see in the NDE to enable the implementation there. And I just want to spend a little bit more time there. So actually, out of the 7 areas, this was selected as the next topic area for a deep dive study, is this non-destructive evaluation. And again, from an academic perspective, it's very interesting scientifically because there's lots of crazy physics going on. We're talking about high-powered X-rays, high-powered ultrasound, very rich digital imaging data streams like I was mentioning. And so this is a really exciting area for us. And again, for industry and for our government researchers, it's really critical to fielding all these new technologies and really harvesting all the innovation and really taking it to the supply chain. So the goal of the study is to identify current emerging challenges and opportunities in sensors, data analysis, automation, and implementation of NDE and metrology. So we'll be excited to report on that in the next year or so. So just last slide here. We've got the reports. Who should read these reports? So as an academic, I find them very valuable to come up with new research topic ideas. I see a lot of program managers in the audience. I hope that you'll read these and come up with ideas for your programs. And also, academics, I hope you'll consider this in terms of your resource planning and faculty hires and the like. So with that, really appreciate your attention. And I'd like to turn it over to Chris from Lawrence Livermore, who's going to talk about metamaterials.
Great, thank you, Ed. Like Ed, it's a pleasure to be here, and thank you, Sridhar, and all the M4Site staff, Josh, Christine, and everyone for helping put these reports together. I think they're very valuable. So what I did was work with the M4Site team on the topic of metamaterials manufacturing. Let me start by saying what a metamaterial is, for those of you who may not be aware. It's essentially a geometric construct, I'll call it, of material that when you put it together at the bulk scale has properties that you normally would not have in a natural material. So things that don't normally occur, for example, negative thermal expansion, materials that shrink when you heat them up. Materials that have very unique electromagnetic properties, can steer waves, electromagnetic waves, or even do things like cloaking at certain frequencies. So this all comes from the underlying structure of the material, which is essentially artificial or designed and created. So what does that have to do with manufacturing? The fundamental problem is they're very difficult to fabricate and manufacture. So metamaterials really can have cross-cutting impact, and they range now in scope. The term has broadened in scope over the years. Started out really with electromagnetic and optical manipulation of those wave fields, things like antennas, filters, things we call super lenses that allow you to see things below the diffraction limit of light. They have major impact in the areas of acoustics, and then in the more mechanical areas, such as lightweighting of structural materials, being able to create materials that have very unique mechanical properties, as I mentioned, things like a negative thermal expansion or a property known as negative Poisson's ratio, which is a really interesting and exciting one, where when you pull on a material, it normally gets skinny. For example, a negative Poisson's metamaterial would get fat when you pull on it. So these are negative, unnatural properties. And they have many applications across defense, national security, energy, healthcare, where metamaterials can have a great impact. However, the primary problem is, again, they can be challenging to manufacture. So we also coordinated and organized through M4Site a workshop with really the goal of identifying recommendations that we could make and put in one of these reports to enhance U.S. manufacturing competitiveness in the area of metamaterials, to really support national security, economic competitiveness, and the like. So really, the key thing that is missing again is scalable manufacturing for metamaterials. These metamaterials are very unique. They can have features down at the micro and nano scale in components that need to be the size of this table. So very broad length scales. They can span many material classes, which make them very challenging to fabricate. You do see a lot of these demonstrations in the news and in the academic literature. However, they tend to be more demonstrations and prototypes haven't really made it to the stage where they can be mass manufactured and produced at scale. Hence, scaled manufacturing is really the missing piece here in metamaterials. And so M4Site put together a lot of these really important numbers and that show that the United States is at the forefront of metamaterials research, and we're poised well to take advantage of it if we take action soon. So what you see there on the left are some of the research investments and citations showing that the U.S. still leads the world in citations in metamaterials, although there are quite a few other large players. And the market potential is growing and expected to be in the multi-billion-dollar range, 3 to 4 billion according to these projections around year 2025. But again, as you see on the lower right there, things like that large roll of material. How do we make metamaterials on, say, a roll-to-roll scale or a large panel scale so they can really be deployed and utilized? As with all of the M4Site workshops, we took input from the community. And similar to what Ed showed, we had a very similar breakdown at our workshop. I chaired the workshop, and a few people in the room were even on the steering committee. And we had a good mix of folks from some of these companies that you see listed here, GM, Lockheed Martin, Raytheon, Applied Materials, good representation from government, national labs, as well as DoD organizations and DOE, and many academics who are very engaged in this, who publish a lot of papers and work with a lot of and spin out a lot of startup companies. So it's a really good mix of folks. So we identified some of these barriers to manufacturing of metamaterials, and you see some examples here. First and foremost, scalable process technologies. We have all these exquisite processes now where we can make very fine features, very unique structures, but you can make a few millimeters of it or a centimeter of it, and it costs you thousands of dollars to do it or more. So really, what are the scalable technologies that need to be advanced to make these kinds of structures more realizable? Metrology, measurement, and modeling and simulation are also key in this area. So these are very complex structures to model and simulate. And like Ed said, we also identified non-destructive evaluation as a key piece here. How do you take a component the size of this table that has nanoscale features in it and really take a look at it and measure what you fabricated and know that it's actually going to work in the field? Those are very hard measurements to do. They're very hard to do. They're very costly, and they take a long time. And fast, scalable NDE would be a key aspect of moving metamaterials forward. Also, feedstock materials are critical here. So again, materials and manufacturing going hand in hand. So what we put into these manufacturing processes to make metamaterials can be very unique nanomaterials, very high quality substrates, and the supply chain for these is not necessarily robust. There are many companies out there that make nanomaterials, and you can acquire those nanomaterials. They tend to be very small companies, and they send you a spec sheet. And if you've ever worked with a nanomaterial before and you characterized it, the spec sheet and what they sent you usually don't match. So the quality of those materials are really important. And again, being able to scale those up. Nanomaterials suffer the same problem as metamaterials. You can make milligrams of exquisite material, but if you need kilograms of it, the scale-up process can be daunting. And in fact, the quality goes down as you scale up the quantity, typically. Other barriers include the community itself becoming more cohesive and collaborative, as well as access to really high-end equipment, tools, and computational capabilities. A lot of those really pushing metamaterials and metamaterials manufacturing industrially tend to be smaller startup companies that don't have access to these sorts of resources. So working with government and FFRDCs and federal labs could be a key aspect of this as well. So we came up with some actionable recommendations for our metamaterials report, which is over here on the table. First of all, a research initiative on process barriers, including things like scaled manufacturing, multi-material manufacturing, measurement and metrology, and simulation. And I'll dive into each one of these a little bit. Again, feedstock quality and availability, having some sort of center of excellence to bring all of this together, and access, again, to federal facilities and high-end equipment and computing. And finally, road mapping and expert guidance are going to be key in this area as well. So really, some of the areas we touched on, we had a lot of experts in processing at the workshop, experts in each of the areas you see listed, and these kind of bubble to the top as some of the key areas that could make a real difference. Things like roll-to-roll manufacturing you see on the top there, and roll-to-roll can go with any one of these technologies. Stepping technologies where you move step in space to make patches of material combined with roll-to-roll. Nano-imprint lithography, which allows you to get nanoscale features over wider areas. Pattern transfer, moving patterns from one substrate to another. 3D printing and additive manufacturing is also key here. Many of these structures are highly three-dimensional. And self-assembly, which is an area where the material itself assembles into an underlying structure that can be unique. And synthesizing those sorts of materials is also an aspect of this. For multi-material metamaterials, there are many metamaterials where you need more than one material constituent in order to make it work. You see on the upper left, that's an example of a negative thermal expansion material. You need two materials plus void space in three-dimensional space in order to make something shrink when you heat it up. And that's a very daunting fabrication and manufacturing challenge. On the bottom, you see a more classical electromagnetic metasurface. And often these are also three-dimensional structures. But you need conductive materials combined with dielectric materials in one structure in order to make this work. So multiple materials in a single structure are really key to making some of these metamaterial concepts happen. And manufacturing multiple materials simultaneously can be very challenging. Joining of those disparate materials, how do you make them want to join? Efficient multi-material manufacturing processes are all key. Again, metrology and measurement. What you see on the left is an example of a metallic component that's 5 to 10 centimeters in size, but has nanoscale wall thicknesses and microscale features built into it in 3D. How do you measure that geometry? How do you understand you built it correctly? How do you do that in a cost-effective manner? And how do you do it quickly? Key challenges, again, holding metamaterials back. You can fabricate and manufacture all you want, but if they don't meet spec and they don't perform, it's a waste of time. So really understanding what you've manufactured is key. It could also benefit from things that, like Ed mentioned, in situ diagnostics, things of that nature in these manufacturing processes. Simulation and design, also key. We're talking about some very high-end, high-performance structures here, and really understanding how they're going to work. We can design some of them now with some of the codes we have available, but really doing that faster and better and getting more people access to these codes and simulation capabilities is key. They can be high-performance computing problems. We're talking about three-dimensional structures, multi-physics in many cases. How do you optimize for, say, structural stability as well as electromagnetics, and again, multi-material. Those sorts of design concepts really take a high-performance computing platform to solve. Feedstocks, I'll mention again. You see on the left some really nice examples of nanomaterials that were fabricated in sort of an academic or national lab type setting. You can make milligrams to grams of these. You see those tiny little cubes, pyramids, and wires all have key attributes that you might incorporate into metamaterials. But again, you can't get them in quantity and quality. So how do you do that? We need materials that have the right properties, things like plasmonic properties. We need scalable material synthesis processes so we can take those milligrams and make many kilograms and maintain the quality. Substrates, as I mentioned, are key as well. Often with metamaterials, you need to build onto a very flat, precise surface or a complex curvature. But those surfaces need to be near perfect. If you have a defect in the surface as you're building the structure up, you're going to have a defect throughout the structure. And with these sorts of metamaterials, that could be a flaw that you can't tolerate in many cases. So access to unique and high precision and high accuracy substrates is really key as well. So how do you do that? How do you get access to those? This is one of those chicken and the egg problems. There's not a huge market demand for these materials. Consequently, no one's really looking very much at how to scale them up well. At the same time, the market is held back because they're saying we can't get the materials. So this is an area where the federal government could play a unique role. And access to federal facilities and experts. There are many FFRDCs around the country, both within DoD and DOE, that have exquisite laboratories and extremely high-end equipment, both at Lawrence Livermore, at Oak Ridge National Lab, Argonne. Many of these laboratories have high-end fabrication and manufacturing equipment that the rest of the community could take advantage of. Additionally, they have exquisite measurement tools, things like beam lines, where you can really understand the structures you've made at a very fine scale. And finally, high-performance computing and computing capabilities. So you see listed there at the bottom the HPC4 programs, which have been very successful, I think, within the DOE. HPC for manufacturing being one, where the Department of Energy goes through a proposal process where a company and a national lab researcher write a proposal together to solve an industry problem using high-performance computing. And if we can apply those sorts of things to metamaterials manufacturing, we could perhaps accelerate its advancement through the so-called Valley of Death. Center of Excellence would also be beneficial, where we could coalesce this community, work on things together, such as communication, translational research technologies, shared equipment, shared resources, computational resources as well, computers, codes, and the like, and co-develop those things. Have some sort of pre-competitive activities with some shared intellectual property if possible. And finally, workforce and training is always key in all of these manufacturing areas. And road mapping and expert guidance. Having a panel of experts from industry, academia, and government that help guide this going forward. Identifying what are the most key application areas, ensuring that the research, the early stage research, the TRL 1, 2, 3 type work is really use inspired and driven toward applications, as opposed to just a bunch of research papers. And so an expert group like that moving this area forward, I think, would be key. Obviously, interacting with some sort of center of excellence or maybe hubbed out of that center would be a possible way to do it. So I'm going to conclude with that, my briefing, and again say thank you to M4Site and all of you for coming. It was a really a great experience to work with them and work with the community to put this report and these recommendations together. With that, I'll pass it off to Dan, who's from the Air Force Office of Scientific Research.
Thanks very much. So I'd like to also start by thanking the folks at M4Site. Been a pleasure to work with them. I learned a lot, great deal of knowledge and professionalism and passion bringing all this together. Also like to thank my previous speakers. You've covered a number of topics in my talk as well, so I can see common threads. I'd like to thank all of you for showing up as well. So in a short period of time, there are 3 points that I'd like to leave with you. First point is that high entropy alloys are a completely new way of making materials that's fundamentally different from the way that humanity's made materials for the last 5,000 years. Second point is that the country that first masters high entropy alloys will have significant economic and manufacturing benefits. And the third, that the magnitude of the problem is huge, and I think will require coordinated effort, not just within any particular department, but across many departments, and in particular, activities within the U.S. have already established expertise in Department of Energy, Department of Defense, and Department of Commerce. So I'm going to start by introducing high entropy alloys. Many of you probably aren't familiar with what they are. So I'm going to describe what high entropy alloys are by putting them in the context of the entire human history of alloy development, and I'll do that in just one chart. So it's a simple story. About 5,000 years ago, the first alloy developer took a chunk of elemental copper and put in a small amount of tin, just a few percent, and made bronze. And humanity's used exactly that same approach for making alloys ever since. It's a simple idea. You start with an element that has some attractive properties, and then you add small amounts of other elements to improve the properties. Copper was the first elemental alloy base, followed a couple thousand years later by iron. And then as the additional elements were discovered, one by one they were exploited until the 1950s, the last commercially exploited alloy was developed, the titanium-based alloys. So it's been, since then, the last 70 years or so, what have we been doing? This approach has become very sophisticated.
So we now control the alloying additions to tenths of a percent or even hundredths of a percent. We control impurities to maybe 100 parts per million. And while the first alloys had only one alloying addition, alloys today, commercial alloys that are manufactured, can have 2 intentionally added elements, or 3 or 4, or as many as a dozen. So it's become rather sophisticated, but it's still exactly the same approach. And in fact, nearly every alloy manufactured today has 80% or more of a single dominant base element. So there's nothing wrong with this approach. It's been very successful. It's changed the courses of civilizations from the Bronze Age to the Industrial Revolution to the Aerospace Age. These lightly alloyed base elements have literally changed civilizations. But there's a problem. There are signs that this approach is starting to reach limits. So, for example, there are no new stable elements that have been discovered in the last 70 years. So the alloys that we're working with today, they're the same base elements that we had 70 years ago. And in a growing number of cases, efforts to improve the properties of those alloys for manufacturing needs have failed. And they failed after decades-long intensive international efforts. These include major activities that went on for at least 3 decades to increase the use temperature of structural metals for energy conversion, power generation, and aerospace transport. It also includes decades-long efforts to reduce reliance on strategic elements, including rare earth metals. And it also includes efforts for at least 2 decades to make practical, functional materials like thermoelectric materials. So these failures are fueling the concern that the ability to manufacture new materials is reaching a limit, and that some fundamentally new idea is needed to move things forward. High entropy alloys is a major new idea that does give us a leap forward. And I'll describe it like this, and I'll draw your attention to the picture there. Rather than making a base alloy that's based on a single element, high entropy alloys have concentrated blends of 3 elements, or 4, or 5, or 6, as many as 8 principal elements. That's your new alloy base. And since there are 60 or so metallic elements to choose from, the number of possibilities is enormous. So let me just put that in perspective. After 5,000 years of using the old approach, humanity's come up with less than 20 base alloys systems. 2 of them are shown here: iron-based, aluminum-based, nickel-based, titanium-based, and so on. However, high entropy alloys offers over 170 million new alloy bases. And if we consider high entropy ceramics and high entropy intermetallics for functional applications, the numbers are just staggering. So it's this huge number of new possibilities that is the distinguishing and major attractive feature of high entropy alloys, but it's also one of the major barriers, as I'll talk about in a moment. So, so there are almost 200 million new possibilities, but the question is, are the properties the same, or are they really better? And the high entropy community is showing some pretty amazing properties for many of these alloys. And these new properties are enabling the possibility of new manufacturing capabilities based on them. And I show here just some of the major industrial sectors that may benefit from some of the properties. High temperature materials for power generation and for aerospace propulsion. Lightweighting materials for efficient transportation. I mentioned functional materials, solid state cooling and heating from thermoelectric materials. The medical field stands to benefit, and industrial applications as well. But as I said, there are challenges as well. And a workshop was pulled together on this topic to make recommendations to enhance the manufacturing competitiveness around these materials. And Chris did a great job of describing the problem that they're working to address. He's dealing with complexity, and he did a great job of showing the geometric complexity that they're struggling with. In high entropy alloys, the manufacturing activities that we're interested in are geometrically simple but compositionally complex. So the challenges introduced to manufacturing for the high entropy field is from the compositional complexity. So as you've seen on the other charts, M4 site organized a wonderful workshop on the topic. Strong industry participation, again, about half the participants from the energy sector, aerospace sector, the medical sector, and primary metals manufacturing sectors were all very strongly represented. I also want to point out that the people that were at the workshop represented the top tier of talent across the United States. We had senior technical fellows from major corporations, members of the National Academy of Engineering, presidents and co-founders of small businesses, chaired professors, senior scientists from government laboratories, and corporate strategic analysts. So it was a very dynamic workshop, and as you heard from the other activities, we through the moderator discussions, we came up with, first of all, the major barriers. I list the 8 barriers that our workshop came up with here. 3 of them focus on the ability to identify the most attractive alloys for manufacturing, and 5 of the activities here focus on the manufacturing challenges that come about from the compositional complexity. So once again, the intent of the workshop was not to identify the problems, but also to identify actionable recommendations to address those challenges. I have fewer than the previous 2 speakers, but you'll see some similarity in the overall theme as well. So the 4 recommendations are shown here. The first is a research initiative on the manufacturing technologies. Second one is a national testing center, again, similar to what you've already heard. Developing a central database and enhancing collaborative efforts. These are in the report. Again, copies of the report are here. You're encouraged to take one. And it's also available for download online. I'm going to spend the next few minutes just going through some of these. Or I'm going through all of them, but I'm going through them rather briefly. So the first initiative, or the first recommendation, was a research initiative on manufacturing technologies. There were 6 particular topics listed here. 2 of them, the one in the upper left and the one in the lower right, have to do with accelerating the process of identifying the materials that have the most attractive benefits for manufacturing. The other 4 topics focus on the manufacturing processes of these compositionally complex materials. So with over 200 million opportunities to choose from, it becomes a daunting task to identify which alloy you want to melt and manufacture. And so 2 major activities that need to be put in place are new experiments, new high throughput experiments, and new modeling capabilities to help accelerate that process. And these experiments and these modeling capabilities need to be tightly integrated to move this through quite quickly. The Materials Genome Initiative has been around for some time now. There are folks in the audience who've helped move that forward. And that has laid a great foundation for the high entropy field to draw upon. But I want to emphasize that the magnitude of the problem brought to the table by the high entropy alloys is significantly larger than the MGI, Materials Genome Initiative, was intended to address. They're working to decrease the time to manufacturing by maybe a factor of 2 or 3. But the high entropy field, as I've mentioned, has increased the number of potential alloys by 7 orders of magnitude. So this is a pretty significant challenge that needs to be addressed. In terms of manufacturing, I list here 3 major activities: melting, casting, and thermomechanical processes. These are standard manufacturing methods that not only shape alloys into the desired form, for final products or intermediate products, but they also change the internal structure of the alloys and give them better properties as well. So there's a lot of knowledge and know-how that's been developed for the lightly alloyed materials that I talked about before using these manufacturing techniques. The high entropy alloys now challenge these conventional processes. In many cases, the high entropy alloys have many different elements that may have much different melting temperatures, for example, and different vapor pressures that make conventional melting techniques more challenging. The high entropy alloys may be more reactive in the molten state, and so casting them and having a mold containment that isn't reduced by the metals and doesn't introduce impurities is also a challenge. And so there's a significant amount of manufacturing research required to develop, for example, new melting techniques such as electromagnetic induction or directed energy induction, new casting techniques. I mentioned Rio casting, but there are other conventional casting techniques that may need to be modified to manufacture high entropy alloys, and then a number of activities in the thermomechanical processes. These are forging and rolling and other such processes. The other aspect of this first recommendation that addresses manufacturing should also focus on additive manufacturing processes. So we've heard a little bit about this today already. In this approach, we form complex shapes from wire or powder products. And so manufacturing advances need to be made, first of all, to produce at scale the high entropy alloys in either powder form or in wire form. And then the manufacturing techniques that are being developed for conventional alloys need to be modified. For example, many of the additive manufacturing processes have 1 or 2 powder feeds because we have a base element and 1 or 2 alloys. But if we have 3 or 4 or 5 or 6 high concentrations of other elements, we need to consider modifying those additive manufacturing processes to allow a larger number of powder feeds, or in the case of coating techniques, larger number of deposition targets. So that's the first recommendation. The second recommendation is to establish a national testing center. We've already heard about this a little bit already. The ability to characterize your manufactured materials, or to characterize the materials that you want to manufacture, requires specialized equipment, and it often requires a specialized staff. These are barriers to the manufacturing field. They represent high levels of investment needed before you start to get returns on investment. And so establishing a national testing center that would be accessed by researchers and industry alike could remove that barrier to manufacturers and provide high quality equipment and knowledgeable staff to help move things forward. Central database is also important. At present, with so many different alloys possible and so many being studied, it becomes difficult to track the data being generated, to track the pedigree of the data, and then to use that to best benefit. There are ways that can be done to, for example, data mine the data if you know the pedigree, the impurities, and so on, and putting that in a central database would allow access to those new tools. And so the major features that this central database would enable is not only collecting the data, but then qualifying the data through different modeling and analytic techniques, and then organizing and providing access to that data, again, to the manufacturer so they don't have to face that as an additional barrier to moving forward. And then the final topic, the final recommendation was to enhance the collaborative efforts through road mapping activity we heard mentioned before, so road mapping and forming a national advisory group to focus on the work that needs to be done to ensure that there's no unnecessary duplication and to make sure that there are no critical gaps in the national effort within the United States. Again, this would also enhance access to federal resources, also for small and medium businesses as well. So I think that's all I have, and I have no one to introduce, so I'll turn it over to Josh, and I think there's time for discussion.
I'd like to start off by thanking all of the speakers for their wonderful presentations, and hopefully everyone was able to glean a bit of information about these topics and how they could be advanced. I figure I'll start off with a question for some of the speakers, and then I'll open it up to the floor, so anybody has a question, please just let me know. So something I could ask Chris and Dan, could you mention 1 or 2 applications of metamaterials and high entropy alloys respectively that might help address some national priorities such as defense or energy?
You want to go first? I can go. So I'll go first. So,
Sure.
So 2 points I'll make. So first of all, it's easy to think of high entropy alloys as a new class of materials, and I would urge you not to do that. It's a new way to make alloys. So it's not a metal alloy, it's not a ceramic material, it's not a functional material, it's not a structural material, it's all of those. if we're using a material to do something now, high entropy alloys is a new way to make new alloys for that application or for that manufactured product. So it's not a single one. However, in the spirit of your question, one of the areas where the high entropy field is focused on most intensively right now is to develop new high temperature structural materials. I mentioned before, the field has worked in this area for at least 4 decades, most of my career, all of my career, unsuccessfully. And so there is now hope that we can extend the operating temperature of metals beyond what nickel-based superalloys currently offer. And this has huge potential for the energy sector, for power conversion, natural gas, coal-fired power plants, steam power plants, and for aerospace transportation, and even, frankly, for internal combustion transportation as well. So there are lots of efforts across the world, and I'm happy to say that in this one particular topic, in high entropy alloys, the United States has the lead, and we are working with a number of industries, the aerospace industry in particular, on this. So that's what I would call out as one of the major things to think about.
So in the area of metamaterials, there are a vast array of applications, but I'll just touch on a few. A few on the more mechanical metamaterial side to start. Light weighting and high strength, high stiffness materials. So complex underlying lattice structures with nanoscale features that can absorb, that are very resilient, can give you high strength, high ductility, and high stiffness for aerospace or other transportation applications. These types of materials can have a large impact. I mentioned negative thermal expansion materials. A really interesting application there might be precision alignment of optics. Many times optics, when they're aligned, as you change temperature, they come out of alignment. And to account for that, you need to have active control, motors, various other corrective optics, etc. Those sorts of things are in, say, a drone with a telescope or a camera in it. If you could eliminate all that hardware and replace it with passive optical mounts that keep everything in perfect alignment all the time, because the material itself, the metamaterial, is changing with temperature. You eliminate all that weight, you increase the range, so some very clear defense applications there. In the area of electromagnetic and optical metamaterials, stealth technology, there's many things you can do there in terms of manipulating the electromagnetic wave spectrum. In the commercial sector, communications, things like antennas that are highly directional and extremely powerful can really enhance communications capabilities.
Anybody in the audience have any questions? Or
So, given the problems that superalloys have presented to the machine tools community, what if any work do you see needs to be done in this community along the same lines? How can it benefit, and how does it cause problems?
So I'm going to focus on the benefit. It of course would cause problems. You mentioned machining, but also thermomechanical processing. High temperature materials are notoriously difficult to form at high temperatures with rolling and forging because they're strong at high temperature. But the path forward, I think, is that there is a small and growing branch of the high entropy field that's focusing on high entropy ceramics, high entropy oxides, borides, carbides, and nitrides. And I think these are showing potential to produce new machine tooling materials for the machining industry, and also new die materials, roll materials, and so on. So, the high entropy concept has the potential of solving its own problems as it moves along in this area. And again, I'll make the point that in terms of the high entropy ceramics, the U.S. is currently the lead in this topic. There's a nice MURI funded from the Office of Naval Research, and they've done some really, really excellent work there.
So my question is regarding proliferation of technology. So each of these technologies give us a lot of advantages, otherwise we won't be doing any research on them, right? So the other point is that we are also trying to do a lot of collaboration with industry and other experts in the area. So what is the mechanism to ensure that these technologies don't proliferate to our adversaries? And so we lose these technologies and somebody else does it.
Well, I mean, I have a thought, so maybe, did everybody hear the question okay? Okay. So one of my thoughts, and we were talking about this as a panel beforehand, is the way technology, manufacturing and materials technology actually gets implemented into the supply chain. So it's one thing to do early stage research, it's another thing to field hardware or software for that matter. And one of the things we were talking about a lot is a culture of prototyping and making first articles and how critical that is to accelerating the whole process. And so kind of the flip side to your question is, well, how do you actually do it in the first place? And I think one of the critical elements is this prototyping, and it might sound, especially maybe to like a venture community, is, you know, that's just a best practice. But in reality, to take an academic technology or to get government research labs into the habit of early stage prototyping and taking some risk, actually making first articles, whether it's a sensor, a new material, Chris talked about it, and scaling up to making kilograms of feedstocks, that's a huge challenge. And so to me, as I think about this from a policy perspective, I think that's the really sensitive technology that companies or you know, the government tends to stamp ITAR on things like that, versus like just a recipe. I mean, in certain cases, I think that can be enabling, but I think a lot of it's around the, how do you actually make something that actually has a particular shape and can be commercially implemented.
Can I try another approach at answering this? It's a very tricky problem. And again, the question was, what can we do to protect the information that we're talking about sharing widely with the audience so that our adversaries don't take advantage of it sooner than we can? It's a very tricky problem, and from my perspective within the Department of Defense, it's something that we're struggling with now. We have mechanisms for collaborating and sharing information between the laboratories and industry, where we acknowledge the need to control information, primarily there because the information is proprietary. We have, for example, the Metals Affordability Initiative. We have a consortium of over 24 major industry partners, and we need to make sure that we protect that information appropriately. But it's a very challenging problem, and my frank opinion is we in the DoD haven't done as good a job as we need to do. Our adversaries are becoming much more adept at gathering information from us, in many cases in places where we put the information out. So I think it takes not only a focused effort on what we do to protect the information, but we need to be thinking differently about what is worth sharing and what needs to be protected. It's a big problem.
Can I follow up on that a little bit, and specifically to Dr. Herderick? So if one of the things we're doing is we're trying to train our researchers that they should be producing first articles, right? You need to think about manufacturability of this thing that you've come up with. And many of our researchers are folks that are from outside the United States. Feels like there's a security mismatch there. Is there a way around that problem? Aside from just giving all the work to Livermore?
Well, that would solve your problem.
Or
No, but I mean,
We'll do it.
well, look, you have to have those controls in place. So again, I can speak from personal experience. So our Industrial Research Center at Ohio State's the only ITAR controlled center at the university. So, and that was, I mean, universities don't operate, I mean, because again, international researchers, they want to publish everything, you know, what was in their coffee this morning, what they're going to have for dinner tomorrow, everything's published or they're not going to do it. So, and part of that, and just to be clear, I mean, so, right, we're US only in the box, and actually a lot of it is around cyber security, right? So Dr. Koga talked about that. I mean, that's a lot of the requirements for ITAR now. So it's not, I mean, part of it is what you share, part of it is where you store the data. But look, it is a culture change. And I mean, sensitive technologies, you know, I guess my point would be there's an existing framework, and we have to strengthen that existing framework of what we already have, whether it's ITAR or whatever the other, you know, data handling. I think too, And the prototyping thing is an overall culture change that's already happening. So maybe I think having the conversation, revisiting the conversation about what you share and what's enabling, I think this is a really critical time to do that.
Yeah, it would be kind of stultifying to have the NISPOM all of a sudden slapped onto a whole bunch of university research institutes. So,
I just want to add that this is clearly a very tricky problem, and it's a cost-benefit kind of thing, right? Having a collaborative community we benefit from. We can move a lot faster when we do that. But obviously, technology diffusion is going to be a huge issue. So I don't know the answer, but I think Ed is completely right that thinking a little bit more carefully and earlier about export control and how we're going to do that, and getting those experts in the room to have those conversations. DoD, DOE, Commerce, I think typically are the three that deal with that or sort of grapple with it. But I think having those conversations early as a field develops is really critical.
So I am in academia, so I'm interested in expanding the knowledge base. So is it your sense, and the question is to all panelists, that we are graduating enough young minds here in the US to continue on the efforts? How do we get students excited about material science? I was supposed to bring in 2 graduate students of mine, but they had classes this morning, so they couldn't make it. So is it your sense that we have enough young, bright people working in this field?
So I'll say from my perspective, in our laboratories at Livermore, where we do a combination of additive manufacturing and architected and metamaterials, attracting folks to that field has not been difficult. They've been flocking to it. I think it's one of the hot fields out there right now. But more generally to material science, I think the answer is we probably still have a dearth of people coming out of the universities. I don't know if you guys feel the same way.
Yep. I mean, my biggest challenge is not, there's tons of interest, and the kids are brighter than ever. They know how to do all kinds of crazy stuff. My issue is, do they know how to use a hammer? And I don't mean to be flippant about it. I'm serious. Bringing kids into the lab, can they use a hammer and a screwdriver, right? And I don't mean to get on my soapbox here, but
They write you a Python script to do
well,
that.
yeah. So they have incredible skill in all these, industrial internet, and all the students, regardless of discipline, are really skilled in CAD and things like that.
no mechanical aptitude.
Well, and so what struck me when you asked the question, I think about this a lot. So there's this movie coming out about Neil Armstrong, First Man, right, based on the book. It's an awesome book if you've never read it. But one of the things that struck me about that book is goes through Neil Armstrong's whole life, and they talk about in high school he took a casting class, he took a welding class. So forget about just shop. He was doing metal casting in high school. Now, I'm a metallurgist, so I think that's awesome. But I think, so to your question, I think there's tons of talent coming into the field. I think as a field in academia, we've been slow to get focused on the engineering side versus the scientific side. Does that make sense?
So with that, we have gone
they're
10
gonna
minutes
kick us
over,
out?
and I
Oh,
want to be
sorry.
respectful of your time. But we do have the room here for a little bit longer. We'll invite our speakers to stick around. We invite you to stick around. Please grab a report. I think the best way to keep students in the pipeline is to get these technologies out into factories so there's jobs for them when they have these skill sets. And some of our centers of excellence and advisory groups, I think, will be imperative to addressing some of these early ITAR security systems. So thank you for coming. Please continue your conversations, and we'll hope to see you at a future M4Site event.